Today we will resume from the calculation that we had last time. So going back, we have here we are required to determine the refrigerating capacity in tons of refrigerant. So we assuming a 2% loss of useful refrigeration by heat came from the room and the brine cooler. So let's try to solve that one. So for the refrigerating capacity from the brine, so we have a 2% loss. So we'll be using the equation Q of the brine. So that will be mCp delta T. Okay. So for the mass flow rate, sorry, I write it here down. So that is BV. So this is mass flow rate. I'm gonna change this one into MB. So this one I'm gonna change. Okay, so that will be MB for the mass flow rate. The symbol for that one, or that represents the mass flow rate. So we have 102 kilogram per minute. Then for the specific heat, so given in the problem, so that will be 3.14 kilojoule per kilogram Kelvin. So that will be the specific heat of the brine water. Then for the change in temperature, so we have the 7 degrees Celsius. So this is already the temperature drop of the brine cooler, or temperature rise. So it can be represented as a change in temperature already. Then we have a 2% loss on the system of the evaporator in the brine, so and also in the brine room. So I'm gonna multiply this one by 100, no? So that will be for 100%, so that will be 1. So we have a 2% loss. So 2 divided by 100, we have 0.02. Okay, to just to represent the loss that between the brine and the room. Okay, so let's try to solve now. So let's try to substitute the values here. So we have your mass flow rate, so that will be 102. So that will be kilogram per minute. Then multiply it by the specific heat of the brine. So we have your so this is 3.14. So the units will be kilojoule per kilogram. Then we have your Kelvin for the temperature. Then we have the rise in temperature, change in temperature. So we have 7 degrees Celsius. Okay, so we don't need to add call this sample. We don't need to add 273 to convert this one to Kelvin. For example, this is already the change in temperature. For example, if I have the change in temperature for say 14 degrees Celsius minus 7 degrees Celsius, so this is already 7 degrees. If you're going to deduct this one, you have the value of 7 degrees Celsius. Now if I'm going to add 14 degrees Celsius, so for example, if I'm going to add 14 degrees Celsius plus I'm going to add 273, so I'm going to close parenthesis that one, minus 7 degrees Celsius, I'm going to add 273. Okay, so the same value if you're going to use in the calculator, so we have the same value, which is 7 degrees also. So that's why I did not change this one to Kelvin already, because they have the same value if you're going to apply this one. Okay, so I'm gonna erase this one just only to show you. So this is already a change in temperature. We don't need to add 273. So we can say this is already in Kelvin, so we can cancel out. Then I'm gonna multiply the 1 minus 0.02. Okay, so using your calculator, so we have the value. So I have the value of refrigerating capacity of the brine, which is this is 2000. So 2197. So that will be point 12. So the units will be kilojoule per minute. So we're going to cancel the units here, so that will be canceled out. So we have your kilogram canceled out, Kelvin will be canceled out. So what is left is kilojoule per minute. Then I'm going to convert this one into tons of refrigerant. So we have the conversion 1 ton of refrigerant. So that will be equal to all over to 211. Okay, so this is kilojoule per minute. So cancel the units here. We have kilojoule per minute. Then we have now your heat or the refrigerating capacity of the brine, which is equal to, so we have the value of 10.41. So 10.41, 41.2. So this is now our tons of refrigerant. Now for letter B, so we need to find the rate of flow of ammonia. So remembering from the refrigerating capacity, so for our evaporator, if we're going to look at evaporator, so this is usually the energy balance or the mass balance of the mass flow rate entering from 0.6 and leaving on 0.7. So we have here the change in enthalpy from 0.6 and 0.7. So we can use this one to determine how much is the mass flow rate of the ammonia. So let's go back to our, let's try to solve this one. So refrigerating capacity or from the refrigeration, so we have your QE, okay, then this is, so QE, so this is signifies or represents the load in our evaporator. So looking at one, the load in our evaporator, so the product load or the required you need to cool down is the heat that is absorbed by the brine water, so which your brine water absorbs heat from the storage room. So you will notice here we have your brine water being pumped in the cold storage room, so maintaining the temperature in the cold storage room, and it has a low temperature coming here, then you will have a higher temperature going here, so it absorbs the heat of the room, then higher temperature of the brine water will be going to the brine tank to decrease its temperature by means of a heat transfer from the coil of the evaporator of the refrigerating system. So our load here is the primary load of the refrigerating system is the brine water. So that's why we use it in our equation here. So that's why I use the QE, okay, represents the load of the evaporator, and also it is the refrigerating capacity of the brine. So our equation here, we have your mass flow rate of the ammonia or mass flow rate of the refrigerant. So that will be the energy balance, so the change in enthalpy from 0.6 to 0.7. So that will be H7. I'm gonna write here H7 minus your H6. Okay. Then to get the mass flow rate, so we can rewrite our equations. So we have for the mass flow rate of your brine, mass flow rate of your ammonia, so Ma. So I'm gonna write here Ma to represent our ammonia. So we have your refrigerating load, then all over this is sorry for that one, we have QE, then we have divided by the change in enthalpy from 0.6 to 0.7. Okay. Now let's try to substitute the values here. So looking back from the data that we have gathered previously, so we have your mass flow rate of your brand ammonia, then we have your QE, which is 10.412 tons of refrigerant. So we're going to use this one, 2197.12. So in order for us to cancel the units here, so we have 2197.12. So that will be the units of kilojoule per minute. Then I'm gonna divide this one by the change in enthalpy, 0.7. So we have here that is 1000. So we have here 1445. Then minus the enthalpy 6. So looking back from the values here, enthalpy 6 is equal to enthalpy 5, HF at 30 degrees. So we have 351.45. Okay. Then the units will be kilojoule per kilogram. So we can cancel out the units here. So we have your kilojoule cancel out, kilojoule cancel out. So what is left will be kilogram per minute. So I'm gonna write here, I'm gonna equate this one now. So since we don't have a space here, so using your calculator, we have the value. So I have the value of that is equal to 2.009009. So the units will be kilogram per minute. So we have now the flow rate that is required to push in our brine tank through our evaporator. So in order for us to maintain the load or to cool the load of refrigerating capacity of 10.412 tons of refrigerant.